Today we're going to discuss clocks, and clocks are used in digital circuits to provide timing, just like a clock is used for people to provide timing. And so the trick with a clock is generally a waveform that looks like the one depicted here, and it has a low value, and then it transitions to a 1, a high value, then back to a 0, and then a 1 and back to a 0 in a periodic fashion. So it has a period that's depicted here. We have the notion that it has a rising edge that's going from 0 to 1. That's shown here, and a falling edge that's going from a 1 to a 0. And so we're going to build this little device that generates this particular waveform. You can build them out of logic gates and or transistors and capacitors. The easiest way to do it is a chip that's specially designed for this, and this is called a 555. 555 comes in a package that has 8 pins, and we'll talk about those in turn. And so those 8 pins, then you wire components around to generate the appropriate clock. So the format, and by the way, 555 is an incredibly versatile chip. So we're going to use it in its simplest form. We're going to put a power here, and then we're going to ground here and here. And then we are going to also put power on pin 4. So we're doing that. The thing that controls the time of the 555, in other words, how long is the waveform in a 1 state and how the duration of the waveform in the 0 state, is done by these 2 resistors in this capacitor. And so you pick the values of the resistors and the capacitors, so it gives you the amount of time in the high state. And so what we do is we use this formula that the number of seconds in the high state is equal to about 0.7 times the sum of the 2 resistors times C1. This is a time constant, because what we're going to do is we're going to be charging this capacitor C1, this capacitor over here, through these 2 resistors. And in the low state, how long it stays in the low state is a function of the time constant between using C1 and R2. Why? Because we're going to discharge through R2. So we're using a charge discharge of a capacitor through resistors to determine our high state and low state. And of course, you sum of those, you get the period. And for this example, if we have let me just erase this. If we have a 20K ohm resistor charging a 10 microfarad capacitor, we get a high state of about 140 microseconds. If we discharge through this 10K ohm resistor with this 10 microfarad capacitor, we get a low state of about 70 microseconds. This gives us the sum of those, and it gives us a frequency of about 5 hertz. And so we're going to flash an LED, and I think we know what an LED is from before, but let's just go through and review. An LED is a light emitting diode. And with this light emitting diode, it has an anode and a cathode. Current wants to go through here, so it's forward bias. And when it's forward bias, we typically have about 1.5 volts across the LED. And the forward bias current is a maximum of 20 milliamps. Matter of fact, it would probably be better to say this is about 10 milliamps. So when it's forward conducting, it will generate light. And let me see if I can get this guy to move. There we go. So what we're going to do is we're going to flash an LED. We're going to flash an LED, so we're setting the LED out here. And when this waveform goes up high, the LED should turn on. And so it's down here. This is a current limiting resistor. The minimum, absolute minimum value is about 200 ohms. I would suggest even a 1K ohm would seems to work. So you could put a 1 kilo ohm resistor here as your limiting resistor. If this limiting resistor is too small or too big, the LED will be very dim or not light at all. If it's too small, you just burn everything out. Now, what happens here is that if I use a 10K ohm and a 10K ohm and a 10 microfarad capacitor, we calculated before, that's about 5 hertz. You will not see 5 hertz flashing very easily on this. So you may want to adjust the value of these capacitors so you can see this light blinking on and off, and that's something you'll experimentally determine. Okay, so let's create a square wave clock. Okay, now what we found is that this will have a downtime that's relatively small and an uptime that's relatively low. So it's going to look like this coming out of the LED or out of the 555. What we want to do is we'd like to have something that has the downtime is the same as the uptime. Downtime is the same as the uptime, etc. So we'd like to have what's called a square wave clock. And we do that by running it through a device called a flip-flop. And a flip-flop has a clock, and so this flip-flop will change state on the rising edge of the output of the 555. So every time the 555 goes up, this flip-flop is going to change Q and Q bar, where Q is its output and Q bar is the negative of the output, or the inverse of the output. What we've done here is cleverly taken the negative output, that's the state it's not in, and put it back in to the input. So what happens on the rising edge, this flip-flop will change state from 1 to 0 or 0 to 1. And that says that even if this is not the output from the 555 is not is symmetric. In other words, the low time is shorter than the high time. The output of the 555 will be symmetric because it's only 555, or I'm sorry, the output of the flip-flop is symmetric because the only time it changes state is on the rising edge of the clock. Okay, so we can build a dual flasher, and a dual flasher looks like this. Let's see, is there anything that I need to go over? We're just going to take the two outputs. Well, let's use a transistor to drive the diodes. So we have a transistor here. This is the current limiting resistor for the diode, and so this is like, let's say, 470 ohms. I'm just picking a number that may be a good number. And then what I do is I put a transistor here. This transistor is going to conduct current. Remember, this is called IC. This is the collector current. Only when when Q, the output here, is high. So during this region, the transistor is going to conduct current, which will cause the LED to light. So we would put these in. This is probably somewhere around a 4.7 K ohm resistor in typical applications. And what this resistor does is it limits the current going out of this output to about 1 milliamp. And the reason we want to do it is if we were trying to drive both this diode and this diode off of a single flip-flop, we may find that the flip-flop can't provide enough current to do these. So we're just going to run it this way. Now, setting up the flip-flop means we have to provide power. We have to provide power here. We have to disable two features of the flip-flop, and this is called set and reset. So we ground both of those. We just wire the two pin 3s, which is just coincidence between the 555 and the clock. And then we do this, we take the complement of the output, or Q bar, and we run it back into the input, so it changes state every time the clock goes high along here. So I built one of these circuits. So let's see what it looks like. And it looks just like this. And so, again, you could build a prettier circuit than this, but this is okay for me. Okay, let's see. We got our old friend, the power supply, over here. So hopefully this is something you've built before. This is the input. This is the transformer inputs. Make sure you don't short those. And then we have the 555 here. So this would be your 5, 5, 5. This is pin 8 over here. Here's pin 4. Okay, and so we ground pin 4 is shown through this white wire. We bring pin 8 up to this orange wire, and this is the positive. This is the +5. And so we have this all wired up. And then these resistors, this resistor is a 20 kilo ohm resistor. This is a 20 kilo ohm resistor. And this is the capacitor. So these two resistors and this capacitor are the things that cause the 555 to oscillate or generate the waveform. And it's just, again, it's a charge and discharge of this capacitor through these two resistors. The output of the 555 is shown here on pin 3. It runs through a current limiting resistor, and I happen to pick a 2K ohm, or a 1K ohm. This is 1K resistor, and then into the LED. As you can see, the LED is lit. That just happens to be the time I took the photograph. And then in this case, it's a second later, it will turn dark. It will light, turn dark, light, turn dark. Now, if you wish to make it a square wave, then we would add the flip-flop here. And we would wire the flip-flop. This would be your flip-flop into the into your 555. So that completes the discussion, and it should be a fun little project to build.